We start our program with importing the PyTorch library, and then we select the device we are going to use. So if you have a GPU on your computer, or if you're using, for example, Google Colab, you can set the device to CUDA, or if you're using a normal computer without a GPU, you can set it to CPU. Then we define out our neural network with a linear layer and a nonlinear activation function, which we can comment out on the forward function if we want to test the network without the activation function. This is done as a class such that the network is an object which we can instantiate and initialize in the main part of the program. This is our first experiment, and here we are defining the class. So this is how we can, one of the ways we can build a model in PyTorch. Here we're using linear layer. So in features is equals to 2, out features is equals to 2, and we are using bias. So we are setting bias to true. Here in the forward section, we see that the output just goes through this layer, and we are commenting out here, so we don't have an activation function in this first experiment. And here we can see that we comment, if we remove the comment, we can use the leaky relu, or we can use the relu as activation functions. But for this first experiment, we are going to look just at what the linear layer is doing. So here we define our class, and in the main part of our program, we will generate the data for training and for validation. So here we are defining our training set. So we have 3 vectors, and there we use a PyTorch tensor. And this is how we have our data in PyTorch. They use tensors, and tensors need a special shape depending on the layers and depending on the input. And so you need to pay attention on how to set up the inputs and outputs and the layers and models in PyTorch. So here we are adding the first dimension for the batch. So we have our tensor, and we can see the shape now is 1 by 3 by 2. So we have 3 features, each 3 samples, and each sample has 2 features. So 1 2 2 1 1 1, x0 x1 x2, and this is how we're doing an input for our training set. And our target, as we mentioned before, so we have 1 0 0 1 and 0 0, and we also prepare and reshaping, and we have that the input and the target now they have the same shape. Here we have batch, sample, and features, or the signal dimension. So here's 1 batch, 3 samples, and the signal dimension is 2. Observe that the validation input data contains a scaled version of the training set. Now we instantiate the model, define the loss function and the optimizer. So here is what we are doing. Our model we are instantiating. So this was our leannet, and here leannet. Here we defining our loss. So we are using the mean squared error loss function from PyTorch. So here we are defining our optimizer. We're going to use the stochastic gradient descent, and we will start with the learning rate of 0.1. So we have here our loss, and our optimizer has a parameter is learning rate 0.1. Here we also have 2 choices of optimizers. So here you can see that this add-on optimizer is comment out. So we can replace, we can try which one works better. Next, we let the optimizer do 10,000 update iterations. They are called epochs. So this is what we're doing for epoch in range of 10,000. So the Y predictions is the model of X, so the model produces prediction output. Here the prediction and target are compared by loss. So for every 100 we're printing the epoch and the current loss value. So we see that we start with a high loss, and our loss is decreasing until it's a very small value, and we see that there are no further decrease after a certain point. Here is typical for PyTorch experiments. We use this optimizer 0 grad, that the optimizer sets previous gradients to 0. Loss backward is the optimizer computes new gradients, and optimizer step, so the optimizer updates weights. Oh, this is very typical in a PyTorch experiment. We always have, so we have the forward that we defined in the model. We have here the 0 grad, we have the loss backward, and we have optimizer step. And here we ran our experiment. So finally we'll print out the results on the training set and the validation set and the obtained weights. And we see here we have the loss in training was here, very small loss, but we see that the loss on validation set 0.5. So we see that we didn't do a very good job, because it works really well on training, but it doesn't generalize well. So on the validation set, it's just a very high loss. So each time we execute it, it starts with a different random initialization. Hence, each time we get a different route that the optimization takes, and possibly different results of the optimization. If we get very different results, then it's a sign that optimization got stuck in a local minimum, for example. Observe that we obtain the desired output on the training set, but the output for the validation set doesn't look good. This is reflected by the loss values, as I mentioned before. We have very small value to the order of magnitude of e to the power of -12 on the training set, but 0.5 on the validation set, and this is a very big loss. So it demonstrates that we have a bad generalization.